Hi Math 215 students. In this second video for section 2.1, we're going to introduce matrix multiplication. Alright, so here is our list of outcomes for this video. We'll display this list at the end, but before you leave the video, please make sure that you're able to discuss these things as they're listed here, and let me know if you have any questions. Okay, so we had this slide on in the last video. If we define what we mean, it is possible to add, subtract, and multiply matrices together. Now, in the last video, we talked a lot about adding and subtracting matrices. In this video, we're going to talk about multiplying matrices together. And we started to answer these other three questions in the last video, and we will continue through this video and in the next two, and especially in the next two, we'll finish answering these questions, in particular why division isn't included in our list of operations listed here, and whether there are any other operations on matrices that we should learn. All right, so before we jump into how to multiply two matrices, we're going to talk about some notation that will help along the way. Let's suppose, to begin with, that A is just any matrix with m rows and n columns, like this matrix, for example. If you were to take a look at just a single column of the matrix A, it looks like a vector, right? 1, 4, 2, 5, 3, 6, these could be vectors in R2 because there are two rows. So in general, if you have m rows, the columns of A look like vectors from Rm. Because of that, we often write the columns of A using the notation little a1 through little an, written in boldface to indicate that they are vectors. So we might use little a1 to stand for the vector that looks like that first column of A. Little a2 stands for the vector that looks like that second column of A, and so on. Now, if we write an expression like this, A equals, and then these vectors inside a pair of brackets, what we're indicating is that we will be using little a1, little a2, and so on to stand for the columns of the matrix called capital A. Okay, now we'll use another type of notation. We'll use little a sub ij, where this A is not bold-faced, it's just a regular lowercase letter with two subscripts I and j, to represent the entry of matrix A found in row I, column j. So in the last video, we introduced what we meant by ij entry. And in this video, the new thing here is just the notation. Little a sub ij is another way of indicating that number. And if we write something like this, capital A equals brackets little a sub ij, what we're indicating is that this little a sub ij represents an entry from the matrix capital A. Now, if you were to actually write out all of the entries in some matrix capital A, they would be positioned within the matrix in this way. Across the top row, row 1, we'd have A11, A12, A13, and so on all the way through A1n. Now remember that the first number in the subscript tells you which row you're on, and the second number tells you which column you're in, and so that should make sense. Row 2 is A21, and so on all the way through A2n. Since this is an m by n matrix, our last row would be row m, so the subscripts would start with m on that row. And the very last column should always be the nth column, so n will always be the last number in any row's subscripts. Okay, please take a look at that. Pause the video if you like to make sense of that. But again, this notation little a with the ij, this just indicates different entries inside a matrix capital A. Okay, now we're going to define matrix multiplication, but before we do, there's something we need to check before we even start. And this will remind you of the important note we saw before addition and subtraction. Remember that you cannot add or subtract matrices of any sizes if the sizes don't match. There's a similar condition for matrix multiplication. You can only multiply matrices A and B. You can only do that operation if the number of columns of A is the same as the number of rows in B. So if A has m rows and n columns, and B has n rows and p columns, then it's okay because the number of columns of A is the same as the number of rows in B. But if you write the dimensions for A and B and the middle numbers don't match, if this n is not the same as that n, then you're not going to be able to do the matrix multiplication. So, for instance, we haven't said how to do the matrix multiplication yet, but as you take a look at these two matrices and you ask, is it possible to multiply them, you'd want to check the dimensions. This matrix on the left is 2 rows, 3 columns. It's 2 by 3. This matrix on the right is 3 rows and 4 columns. And because those two middle numbers match, they're both 3, it should be possible to multiply these two matrices together. Surprisingly, on the other hand, these two matrices cannot be multiplied together. It wouldn't make sense because the 3 and the 2 inside here don't match. Now, this is different from addition and subtraction. Remember, with addition and subtraction, you can only add or subtract matrices that have the exact same dimensions. But when it comes to multiplication, we're doing something different, and actually these two matrices could not be multiplied together. Okay, now, why is it important for the number of columns in A to match the number of rows in B? Well, we'll answer that in 2 parts. The first part just has to do with what you're going to do with these matrices. Now, it turns out that when you do multiply a matrix that has the right dimensions, A is m by n and B is n by p, so the middle numbers do match, the outer numbers, m and p, give you the dimensions of the answer. So the product AB, if A is m by n and B is n by p, the product will have dimensions m by p. We take the number of rows in A, the number of columns in B, and that gives us our dimensions for AB. Now, with that bit of information, we can get started. If we were to take these two matrices from before, our 2 by 3 matrix and our 3 by 4 matrix, we know that the inside numbers match. The number of columns in A is the same as the number of rows in B. We also know from our rule here that the outer numbers should tell us the dimensions of our answer. So our answer should be a 2 by 4 matrix. It should have 2 rows and 4 columns. So it should look something like this. We need to fill in the blanks for these 8 entries, but they should be arranged in that format for a matrix. Okay, this is important to identify right at the very beginning. You need to start off knowing what the dimensions of your answer should look like. But then, if you were to do it this technique, which I'm going to introduce now, this is called the row-column method. What we're going to do is fill in these entries one at a time. And the way we'll do that is pick an entry. Say we want to fill in the IJ entry. To complete the IJ entry, to fill in a blank, what we need to do is take a look at the row I it's in and use that row from the first matrix. So for instance, if I wanted to complete the 1, 1 entry, the first one tells me to use row 1 from the first matrix. The second one in the 1, 1 entry tells me I should use the first column of the matrix B. Okay? So row I of A, column J of B. Now, for the 1, 1 entry, row 1 takes the numbers 1, 2, and 3. Column 1 of the second matrix gives me 1, 2, and 4. And what I'm going to do is pair those together. So the first entry goes with the first entry, the second entry goes with the second entry, and the third entry goes with the third entry, and we get those pairs in that way. Now, I'm going to multiply those two numbers together in each case, and that will give me a bunch of numbers. I'm going to add those numbers together and see what I get. So 1 times 1 gives me 1, 2 times 2 gives me 4, 3 times 4 gives me 12, 1 plus 4 plus 12 gives me 17, and 17 is the number that I will put in the 1, 1 entry. Okay? It takes a couple times of practice to get this done, but we'll go through and we'll fill out the rest of the entries for this matrix. We've finished filling in the 1, 1 entry. Let's move on to the entry in row 1, column 2. Now again, because this is row 1, column 2, we're going to take the numbers from row 1 of the left-hand matrix and the numbers from column 2 of the second matrix. So 1, 2, 3, like before, will be paired up with 0, 3, and 5 in that order. And we'll do the same thing as before. We're going to multiply these pairs together and then add the results. So 1 times 0 is 0, 2 times 3 is 6, 3 times 5 is 15, 0 plus 6 plus 15 is 21, and so 21 is the number that should go here. All right, now continuing along, what would happen here in row 1, column 3? Well, as before, we're going to use row 1 from the first matrix and column 3 from the second matrix. So 1, 2, and 3 will get matched up with 2, -1, and 0. And when we do that multiplication, we'll have 2 plus -2 plus 0, which gives us a grand total of 0 for that entry. And finally, row 1, column 4, we'll put 1, 2, 3 together with -1, 0, and -3, and we will add -1 plus 0 plus -9, producing -10. Okay, now the second row of our answer will end up using the second row of the first matrix. So we'll have 4, 5, 6 each time. But as we fill in the numbers from the first column, we'll have 4 plus 10 plus 24, which gives us 38. For the next entry, the second column, we'll use 4, 5, and 6 times 0, 3, and 5. And pairing those up in that way, we'll add 0 plus 15 plus 30, giving us 45. For that third column, we'll take 4, 5, 6 from the first row, 2, -1, 0 from the third column, and we'll get 8 plus -5 plus 0, producing +3. And then finally, this is turning into a long and tedious process, but we'll take 4, 5, 6, multiply it onto -1, 0, -3, and when we put that together, we'll have -4 plus 0 plus -18, producing -22. Now, we asked why it was important that you had the same number of rows in B as you had columns in A. Why is it important that these two numbers match? And you start to see why that is. We're taking the numbers from a row of A and a column of B, and the number of numbers in a row of A is exactly the same as the number of columns in A, and the number of numbers in a column of B matches the number of rows in B. And so for those two sets of numbers to pair up in this way, we need the two middle numbers to match up. Okay. Now, having done this, we have produced the answer. This matrix with 8 different entries in this arrangement is the answer when you multiply this matrix times that one. Now, that was a long process, but hopefully a little straightforward. Here is another example. What I would encourage you to do at this time is pause the video, take a second to identify the dimensions of your final matrix, check to see that multiplication is possible, but then note that the answer should be a 4x2 matrix. So think about what that looks like on the right-hand side, and then try to fill in all the entries of that matrix. We'll come back in a couple seconds. Okay, well, keeping in mind that the dimensions are given by those adder numbers, 4 and 2 give us the dimensions. It should have 4 rows and 2 columns. Again, 8 blanks, but this time with a slightly different arrangement, and we're going to fill in what those blanks are. Now, hopefully you've done this already, but if we just march through, for the first row, first column entry, we would use the first row of the left-hand matrix, the first column of the right-hand matrix. We'd get -2 times -3, -1 times -2, and 0 times -1. And that gives us 6 plus 2 plus 0, producing 8 as the number that goes out there. Moving along to row 1, column 2, we'll take the same numbers, -2, -1, 0. but this time we'll pair them with 4, 5, and 6, which are the numbers in the second column in B. We'll get -8 plus -5 plus 0, which produces -13. Okay. Now, in the interest of time, I'm going to just kind of flip through the rest of this multiplication. Please feel free to pause the video or go through it slowly, as slow as it helps you to do. But filling in the entries, the next one will be 2. One after that will be 2. The third row first entry would be -4, and the third row second entry will be 17. For the fourth row, we'll take the fourth row of the first matrix, and then pairing that with the numbers from the first column gives us -10. Pairing that with the numbers from the second column gives us 32. And this is our answer when we multiply these two matrices. Okay? Okay, so this is the row-column method for multiplying matrices together. Now, at the beginning of the video, we introduced some notation. Here's one place where the notation comes in handy. If you wanted to carefully and concisely write this multiplication rule, you could write something like this. Now, I've labeled it as optional because we won't be so intensely focused on the notation. But if you're interested, you might remember the summation symbol. You may have seen it in a calculus class. If we know that matrix A times matrix B equals matrix C, and if we use the little a, little b, and little c to indicate the entries of A, B, and C, then to figure out a particular entry of C, namely the entry in row I, column J, what we're going to want to do is multiply numbers from row I of the matrix A and column J from the matrix B, and we'll do that, and the number of things there will be as many numbers as there are columns in A. That number is n, remember? Okay. So we can get this summation expression for the entries in our matrix C. If you're interested, try it out. Try substituting different values for I and J and see what the summation looks like. But this is a concise way of sort of writing out how to calculate an entry for the product of matrices. Here's an example we just saw. We did see that if you multiply these two matrices, you get this answer out, and we've illustrated what the calculation looks like for the 4-2 entry of C. What you want to do is go across the fourth row of A and go down the second column of B, multiply those numbers together, add the products, and what you'll get is 32, which is shown there. Okay, now there is a second way to find the product of two matrices. It's not going to give you a different answer. It'll be the same answer as the row column method we just talked about, but it's going to be helpful in some situations. So here's the same reminder we had before. You can only multiply matrices A and B if the dimensions of A and the dimensions of B have the same numbers in the middle. That's still the case here. But another way to think about multiplying AB is to think of B as consisting of the column vectors B1, B2, all the way through BP. Remember, B is n by p, so there are p columns, and so p column vectors forming B. And if you wanted to compute A times B, another way of doing it would just take the matrix to take the matrix A and to multiply it onto each of those columns of B individually. We know that when you multiply a matrix times a vector, what you get out is another vector, and the vector we get out in each column is going to form the new column for the matrix AB. All right? So let's see this illustrated with one of the examples we already saw. If you wanted to think of computing the product of the matrices in this way, what you might do is just take the first column of B and multiply this matrix onto that first column. Now remember how we defined a matrix times a vector. We said you're going to take the numbers from that vector and attach them to the columns from the matrix. And when you do that linear combination in that way, if you do this -3 times the first vector, -2 times the second vector, -1 times the third vector, and you add them together, you can check that we get the entries 8, 2, -4, and -10, which matches what we saw before. Now, on the other hand, the second column of matrix B was 4, 5, 6, and if we were to take this matrix and multiply it onto 4, 5, 6, we would form the linear combination you see there. And doing that calculation, we'd end up with -13, 2, 17, and 32. And you'll see that we get the same answer doing it this way as we had before when we used the row column method to compute each of those entries. Now, you can kind of see why that is. Let's take a look at this, this last calculation. If we wanted to figure out what the second column's entries should be, let's just take a look at this entry 2 in the second column. To calculate that 2, we're in the second row, second entry. So if I wanted to do it using the row column method, I might go across the second row and down the second column here and have -1 times 4, 0 times 5, 1 times 6. Now if you take a look at what's happening with this vector calculation, you'll see that in the second position we do have -1 times 4, 0 times 5, and 1 times 6, and that's what you add together to get 2. So the calculations that you're doing to produce that 2 in this position are the same additions and multiplications whether you use the row column method or whether you use the vector computation on the right. You do get the same answer each time if you're doing it correctly. Okay, this way of thinking of matrix multiplication is not everybody's favorite way of thinking about it. The row column method seems to be more popular among students who are first learning matrix multiplication. But it's important to remember this way of thinking matrix multiplication as multiplying the matrix A onto the columns of B. And this will help, especially when we have to answer conceptual questions. For example, pause the video and try to answer this question. True or false, when matrices A and B are multiplied together to form AB, each column of the result is a linear combination of the columns of A. Okay, hopefully you have an answer for that. This would be a true statement. Okay, the reason why is because of what's shown here in the rule. The columns of AB are each formed by taking A times a vector. And remember, when you take A times a vector, what you're doing is putting coefficients on the columns of A and forming linear combinations in that way. So each column of A times B ends up being a linear combination of the columns of A. Okay? Okay, we'll see more conceptual questions later on. This way of thinking about matrix multiplication will help with those conceptual questions. Okay, let's go back to that question of why do we define matrix multiplication in the way that we have? Whether you think of it in terms of the row column rule or whether you think of it as a matrix multiplied onto the columns of the other matrix, why do it that way? I'm not sure if this will be a satisfying answer to you, but trust me that it's important to mathematicians and to all of us that this property hold. What we want is to make sure that however we decide to multiply AB together, whatever technique we use to calculate this, we want this property to be true. Now, this looks like an associative property of sorts. We've kind of grouped the multiplication on the right and then the multiplication on the left. These have different meanings. Okay, the left-hand side is a situation in which case you are multiplying B by the vector X, And we talked in chapter 1 about how a matrix times a vector produces the same effect as a linear transformation. Remember, a linear transformation was a function on the vectors that satisfied some very helpful properties. And matrix times a vector gives you a linear transformation. And so Bx is a linear transformation on x. We are going to multiply the matrix A onto the vector we get out from that linear transformation. And again, a matrix times a vector is a linear transformation on the vector. So the left-hand side shows what happens when you take x, you apply the linear transformation from B, and then afterwards you apply the linear transformation from A. On the right-hand side, though, what we're saying is we're going to take a matrix AB. We have to decide what we mean by A times B, like how are we defining multiplication? But what we'd like to have it be true is that if whatever this matrix turns out to be, we want this matrix to have the same effect on x that these two linear transformations had on x on the left-hand side. All right, now how do we make that happen? Well, let's take the end and start with that. We want to figure out how to define matrix multiplication. If we want this equation to be true, then let's take a look at what the left-hand side means. Now, inside the parentheses, remember that what you end up doing to compute Bx is you take the entries in the vector x and you multiply them onto the columns of B. Okay, so Bx can be written as this linear combination of the columns of B, and then we're going to take A and multiply it onto that result. Now, matrices can multiply onto sums of vectors. I can distribute that A through there. And what's happening in each of these terms is I have a scalar, x1, x2, xp, and scalars factor out in front of multiplications, so it's not a problem if I want to put the A right next to B1 or right next to B2 or so on. So this is a linear combination, and in fact, this looks a little bit familiar. x1 times a vector, x2 times a vector, xp times a vector. This looks exactly like the situation where I have a matrix times the vector x. Now the entries in this matrix, the first column should be A times B1, A times B's first column. The second column should be A times B's second column, and so on. And so if I want this matrix AB to have the same effect as what's going on the left-hand side, I need the columns of AB to look like A times the first column of B, A times the second column of B, and so on through the end, A times the last column of B. And that tells us that actually it's a good idea, it's actually the best idea, to define matrix multiplication in this way. Now, luckily for us, doing it using the row column method gives you the same answers. And so we have two different ways of thinking about matrix multiplication, but we've kind of led you through why we define it in this way. It's so that we can make this property true. Okay, we're going to wrap up the video in just a few minutes here, but we have another definition that will come in handy. The diagonal entries of a matrix are the 1, 1 entry, the 2, 2 entry, the 3, 3 entry, and so on, all the way through the end of the rows and or columns there. These are called the diagonal entries. Altogether, these entries form what is called the main diagonal of the matrix. Okay, the main diagonal always starts in the top left corner and just proceeds down, moving over one entry in each succeeding row. Okay? Now, every matrix has a main diagonal, but there are certain matrices called diagonal matrices. A diagonal matrix is a square matrix. It's got just as many rows as it does have columns. And what makes a matrix a diagonal matrix is that the diagonal entries are the only entries that could not be zero. Every entry that is not on the main diagonal needs to be zero in order for you to have a diagonal matrix. So this is what one sample diagonal matrix looks like. Here are a couple questions for you. remembering what we have said about multiplying matrices, this 3 by 3 matrix should be, I should be able to multiply that onto a 3 by 4 matrix. And this 2 by 3 matrix, I should be able to multiply that onto a 3 by 3 matrix. If you were to do that, what would you get out? And can you interpret that? Can you sort of describe what happens when you multiply a diagonal matrix onto a matrix, either on the left or on the right? Maybe pause the video and try to answer that. Okay, well, here's that first computation. If we do the multiplication of 2, -1, 3, that diagonal matrix, onto the matrix, the 3 by 4 matrix there, here's the answer you should get. And as you kind of compare the entries on the left-hand side with the entries on the right-hand side, you might see some patterns there. The 0, 12, 9, 18 kind of looks like a scaled version of 0, 4, 3, 6, scaled by 3. The middle row looks like the middle row of the other side. It's just that the signs are changed, and that kind of corresponds to that -1 there. And the 2 looks like it got multiplied onto the first row, making it 4, 2, -2, and 10. So it kind of looks like multiplying by this matrix on the left gives you a scaled version of each row for your answer. Now, on the other hand, if we do that other multiplication, where we do the multiplication with the diagonal matrix on the right, we end up with this matrix here, and it looks like the first column is 2 times the first column of the matrix on the left. -420, -20 is 4 times -1, -5, and 18 minus 18 is 6 times 3 minus 3. So it looks like these numbers on the diagonal were used to scale the columns of the matrix that we started with on the left. All right, so what happens if you multiply a matrix by a diagonal matrix? You might guess what's happening in general when you multiply by a diagonal matrix on either the left or the right. And try some examples. See if you're right in your guess. Okay, this leads us to our last definition for the video. An identity matrix is a diagonal matrix in which every diagonal entry is 1. Okay, so remember, if it's a diagonal matrix, it has to be a square matrix. There has to be the same number of rows and columns. Every entry that is not on the main diagonal needs to be 0. And an identity matrix adds the next condition that every entry that is on the main diagonal is equal to 1. All right, so this is a diagonal matrix. We call it I2. The 2 indicates how many rows or how many columns there are. I3 looks like that. I4 looks like that. And these matrices all look alike. They all have 1s down the main diagonal. And we write I or I sub m to indicate these. Now, the identity is important because of this property that we just talked about. What happens when you multiply by a diagonal matrix on the left or on the right? And if your diagonal entries are all 1s, what do you think happens? Well, let's see this in a list of properties that we'll end the video with. Here are some basic matrix multiplication properties. I don't know that any of these should be surprising to you, but it turns out that these properties are true for matrix multiplication just like they were for other kinds of multiplication that you've seen before. It turns out that if you put parentheses grouping the latter terms, A times the quantity B times C, where A, B, and C are matrices, you get the same answer you would if you were to put the parentheses grouping the first 2 terms. In other words, matrix multiplication is associative. If you have A times B plus C, and we're assuming that A, B, and C all have the right dimensions to make this work, then you would get the same thing you would get if you were to multiply A onto B and onto C respectively, individually, and then add the results together. So we can think of A as being distributed onto the B and the C, and the distributive law happens. Now, a similar distributive law happens if the A happens to be on the right-hand side of B plus C. We're not taking any chances here. We have a distributive law for each version, and indeed, A can be multiplied onto both C and onto both B and onto C individually, and then we add the results together. Now, in this property, you'll notice that I'm very careful to keep A after B and after C. That's because the A was after the B and the C in the original version. I'm not going to switch the order of A and B or A and C. I'm going to keep it the same as it was on the left-hand side. Now, we won't say much about that right now, but in the next video, we're going to talk about some things to be very careful of when you're doing matrix multiplication. All right, this fourth rule talks about what happens if you have a scalar times a matrix product. You would get the same thing if you scaled the result, or if you were to scale one of the individual matrices before doing multiplication with the other matrix. Now, keep in mind here that this result says I get the same thing if I scale just one of the two matrices. If I were to multiply R onto both A and onto B, I wouldn't have it equal to just what R would be multiplied onto the whole thing. All right, and then finally, we would go back to our identity matrix. If you multiply A by an identity matrix on the left, what happens? And if you multiply A by an identity matrix on the right, what happens there? And in both situations, you end up getting exactly the matrix you started with as your final answer. This is why we call these the identities. In multiplication, we talk about the number 1 being the multiplicative identity. 1 times any number just produces that same number. And for matrices, the identity matrix plays that same role. Okay, we'll wrap up this video. We have talked in this video at length about how to multiply matrices together. We still haven't really talked about why division is not included in this list. We'll answer that in the very next video. We're going to be talking in future videos also about maybe 1 or 2 other operations that it would be helpful to learn. But with that, we'll display the list of outcomes again. Please take a look at this list, review whatever you need to, and I will see you in the next video.